So, good morning to all of you. I welcome all the KPA members, other invitees, and students to this online seminar today. As you know, we have been conducting these talks for over 2 years now, almost every Sunday, with the intention of educating our members and students on variety of topics, not just the ones in which they have a deeper knowledge. So this is a kind of a continuing education scheme uh, we have developed or we are implementing. We hope that our more and more KP members and students join with us in making this program a good success. We are very thankful to faculty members from colleges, universities, and research institutes all over Karnataka, and even from outside, for helping us out carry out this program of continuing education. So we have conducted talks all the way from the micro world, the world of quarks, all the way to cosmology, and many topics in between: solid state physics, nuclear physics, and spectroscopy, and all that. So our main aim is to encourage people to interact with experts and learn few things, at least in the introductory manner. So today we have a very distinguished speaker from Fermilab, Dr. Pushpalatha Bhat, who has kindly agreed to give us a talk on the discovery of top quarks and Higgs boson. In fact, I must say she was very much deeply involved in the discovery of top quark and recognized as one of the pioneers in that field. So very thankful to you, and we welcome you to this particular seminar, madam. So before I request her to speak for about 15 minutes, followed by 10 minutes of question answer session, I request our General Secretary, Professor Nagaraju, to introduce the speaker. Over to you, Professor Nagaraju.
Okay, sir. Thank you, sir. Dr. Pushpalatha Bhat is a distinguished scientist at the Fermi National Accelerator Laboratory, Fermilab, head of Fermilab Future Collider Group, and an adjunct professor at graduate faculty at Northern Illinois University. After receiving her PhD in physics from Bangalore University in 1982 and a brief stint as scientific officer at the Eindhoven University Cyclotron Lab in the Netherlands. She moved to US and carried out postdoctoral work in experimental high energy physics at Duke University and Fermilab. Her research career has spanned applied physics, nuclear physics, and experimental physics, particle physics from KEV energies to the energy frontier. Since joining Fermilab in 1989, she has led numerous projects, including the successful luminosity upgrades of the Fermilab T Variation Accelerator Complex. She made significant contribution to the discovery of the top quark and the precision measurement of its mass, as well as to searches for the new particle, while bringing a paradigm shift in physics analysis with the use of multivariate data analysis methods. She joined the CMS collaboration at the Large Hadron Collider LHC in 2006, was stationed at CERN 2010 through 2012, and contributed to the detector integration, commissioning and operations, and the Higgs boson discovery. She is an author of numerous peer-reviewed publications, including several review articles, and she has given many invited talks and public lectures. She has organized several international conferences and has mentored numerous students from diverse backgrounds at all levels, but is also an active organizer and a facilitator of outreach to the broader science community, the public, policymakers, and decision leaders. She has chaired and moderated many panel discussions on topics of basic science, research, and innovation, science and society, US Science and Enterprise, and Big Science and International Science. Her panelists have included presidential science advisors, head of national agencies such as NSF, DOE, and NASA, legislators, presidents of universities, directors of national laboratories, Nobel laureates, and many distinguished scientists. Bhat is a fellow of the American Physical Society APS and the American Society Association for the Advancement of Science. She has served at the chair of the APS Forum on Physics and Society FPS and as chair of several committees. She has served on the APS Council and on the APS Board, Directors, AAS Council, and as Secretary for the International Committee on Future Accelerators, that is ICFA. About coming to the schooling, we are very proud that she is from Bangalore only. She studied the primary school, middle school, government middle school, and St. Teresa Girls High School, all in Chamrajpet. So the Chamrajpet people should be proud of her. She is working in the Fermilab. And finally, she studied in National College for BSc Honors, then Central College, Bangalore University. I know that she is the PhD student of Dr. N.G. Puttaswamy. He is also joining for this talk. And of course, she has also worked with Professor Malia at IISc and used many of their metallurgy and spectroscopic computing facilities while working for her PhD degree. With this, we welcome Dr. Pushpalatha C. Bhat. Madam, over to you.
Thank you very much, Professor Nagaraju, for that very generous introduction. Thank you, and hello, everyone. Good morning. I hope it's not too early on a Sunday morning for you. It's 10 p.m. here in Chicago, and it's 15 degrees below zero in Celsius here. So, but I'm very pleased to be talking to you. And for those who are joining from outside India, good afternoon or good evening from, whatever applies from the place you're joining. And I'm very pleased to talk about the discoveries of the top quark and the Higgs boson today. These were landmark achievements and monumental discoveries in particle physics. And I was privileged to be participated in these both of these discoveries. So the pursuit of the top quark and the Higgs boson is actually the continuation of humanity's age-old quest to understand our universe. To answer questions,
please continue.
To answer questions like what's out there in the vast cosmos in our universe, where did we come from? And what is the world made of? What holds it all together? So those sort of questions. And of course, what's out there and what in the vast and mysterious universe of ours is the realm of astronomy, astrophysics, and cosmology. High energy or particle physics, which is my field, seeks to probe the universe at its scale. What are the basic building blocks of matter? That's the central question. What are elementary or fundamental particles? And how do these fundamental particles interact with each other? How does nature behave at its most fundamental level? And can what we understand about these building blocks, can this explain the existence and evolution of the universe? Of course, our ancestors thought that everything in the world is made up of 5 elements. So this quest for the building blocks is as old as humanity. Indian scientists, philosophers hypothesized that everything is made up of the Panchabhutas, air, water, earth, fire, and space. Greeks had 4 elements. And from those 5 elements of the ancients, over hundreds of years of alchemy and chemistry, we arrived at what's called the periodic table of elements by the end of the 19th century. And then understanding of the atomic structure the modern atom began soon after with the discovery of the electron in 1897 by Thomson and the nucleus in 1913 by Rutherford. If you probe much deeper to find out what is elementary, really what is the most fundamental building block, we have found that the atom is made up of nucleus and electrons around it. And then the nucleus itself is made up of protons and neutrons. And even the protons and neutrons have tinier particles called quarks. A model for the quark theory was proposed by Murray Gell-Mann and George Zweig in 1964. And in fact, I met George Zweig after the discovery of the top quark. I also want to have a side note here that when I'm talking about these particles, the masses of these particles, we kind of measure and express it in units of energy because E equals mc square, and that's an important thing in particle physics and nuclear physics. And so I'll be talking about electron volts or million electron volts, MeV or GeV, when I talk about particle masses. Just as examples, the electron mass is about half an MeV, 0.511 MeV. Mass of the proton is about 1 GeV, just so you keep that in mind. Now, to see different sized objects, we use probes which have wavelengths that are compatible with the size of the object that we want to probe into. So if you look at the scale from the vast objects in the cosmos, where you use telescopes of various types, and then eventually to look at the cells and objects of that order, you'd be using microscopes, and then you use electron microscopes or smaller ones. And when we get to the subnuclear, subatomic and subnuclear world, then we have to be using particle accelerators as our main gadgets. Because the smaller the objects, we need probes of smaller wavelength in order to see these small particles, but also we need high energy particles as probes, not only as probes, but also we need high energy to be able to produce new kinds of particles, which I'll talk about when I talk about collisions. So our ordinary world, everything that we see around and ourselves, we are made up of protons, neutrons, and electrons. And as I said, protons and neutrons themselves are composite, and they're made up of the so-called up and down quarks. So I've illustrated that here. And then you have electron, which is necessary to create atoms. And photon, is the quantum of light. And then we have electron neutrino, which shows up in beta decay. It's the carrier of weak force, while photon is the carrier of the electromagnetic force. The existence of quarks themselves was experimentally proven by deep inelastic scattering of electrons from protons at the Stanford Linear Accelerator in 1968. Now, so as we, so these quarks, up and down quarks that I talked about, which make up protons and neutrons, which are sufficient along with electrons and neutrinos to explain our ordinary world, they form what is called the first generation of matter particles in the grand theory, the so-called standard model of particle physics now, which was built over the last century, most of the last century, I should say. But it turns out that the first generation of particles wasn't enough for nature. So there were 3 generations. There are 3 generations of matter particles. The second and third generation seem to be like heavier cousins of the first generation, but they have different masses and therefore are interesting in their own right. So I show here these kind of building blocks, which show the matter particles on the left side, the quarks, and then the leptons in 3 generations. And then we have the so-called force carriers, or gauge bosons. Photon is a familiar one, and then we have gluon, which is the carrier of the strong force. W and Z are called electroweak bosons. They are the force carriers for the electroweak interactions. So the standard model is a quantum field theory which incorporates these three generations of quarks and leptons and three forces: strong, electromagnetic, and weak. And also it needed a special particle called the Higgs boson, or the Higgs field, which we'll come to later on. The up and down quark, electron and electron neutrino, as you know, we kind of knew at the turn of the 20th century. And then we found particles like muon and the strange particles in cosmic rays, cosmic radiation. And after that, we needed particle accelerators to be able to discover and to study other particles like charm, bottom and top, and tau lepton, etc. So particle accelerators have played a crucial role in the establishment of this magnificent theory, the so-called Standard Model of particle physics. So now I want to step back and just look at the Standard Model circa 1975, that is 50 years ago. So what we knew at that time was we had the first generation quarks and leptons. We had the second generation complete, and then the tau lepton also had been found at that time. There were three of the third generation particles missing. And then we did not also, in the laboratory, we did not have discovered the strong force carrier gluons and also the electroweak ones. So this was the status then. And of course, the Higgs boson was the Higgs mechanism had been proposed in 1964. But at that time, it was urgent and important to look for other particles that needed to complete the matter particles and the force carrier particles. So the bottom quark, or the beauty quark, also called simply the B quark, was discovered in Fermilab. That was one of the first major discovery. In 1977, Leon Lederman, who was the second director of the lab, and his group discovered the B quark at Fermilab in a proton nucleus interactions. So this kind of gave more impetus that there has to be a third generation of quarks, and so top quark must exist. The beauty must have an isospin partner, and so you need to have a top quark, and it was necessary then to go on a pursuit of the top quark. The tau neutrino also, of course, was required to complete the lepton doublet, even though it was kind of indirectly inferred that, of course, when the tau lepton was there is an associated neutrino that should exist. So by the end of 1977, after Leon Lederman's experiments, the bottom quark was found. So we filled that gap. And then by 1990, there were other particles that were discovered. The gluons were discovered in DAISY, at DAISY laboratory in 1979 at the Petra Collider. This is in Germany. And then the W and Z bosons, the electroweak gauge bosons, were discovered at the proton-antiproton collider at CERN, which was a lower energy collider than the Fermilab Tevatron, which came into being around the same time. So in 1993, the W plus minus and the Z bosons were discovered. So we filled a lot of these gaps that we have. And so the race for the top quark began. That was the most important thing to find after the B quark and the electroweak bosons had been discovered. So this was I'll go through just a couple of slides of the pursuits of the top quark searches all over the world. The top quark mass was inferred at that time to be about 15 GeV. Based on the measured mass difference between the charm anti-charm bound state and the bottom anti-bottom, or BB bar bound state. So they thought that if there is a top ponium or top anti-top bound state, it should be about 30 GeV, and so the top mass would be about 15 GeV. So the searches at T plus E minus colliders at DAISY, but the Petra collider kind of assumed that the top should be quite light, 15 GeV. And so they looked for the top quark. There was no sign of the top quark, and they set a lower limit on the mass of the top quark of 23 GeV. So what that means is that the top mass should be higher than 23 GeV. Then in Japan, Tristan collider, another E plus E minus collider, was built specifically to search for top quarks. Again, there was no top signal found. And again, there was a lower limit on the top mass that was set of 30 GeV. At the LAP collider at CERN, as well as the Stanford Linear Collider, various precision measurements were made on the W using the W and Z bosons, and these actually provide some indirect constraints on the top quark mass. They also can look for the Z boson decaying into top and anti-top pairs directly, and the Z boson mass is about 90 GeV, so you can set a limit of the order of 45 GeV, and that's what they did because they found no signal for top quark even at LEP and SLC. Then, of course, there were top quark searches at the Hadron colliders, that is proton, anti-proton colliders, which were developed in the early 1980s, both at CERN and Fermilab. Carlo Rubbia first proposed that we build these proton anti-proton colliders to be able to look for new particles. So SPP bar S at CERN, which hosted the UA1 and UA2 experiments, which made, of course, the major discoveries of the W and Z bosons in 1983, also looked for the top quark. In 1984, in fact, UA1 experiment that was led by Carlo Rubbia reported evidence of top quark with a top mass of about 40 GeV. And with more data and analysis, the signal just vanished. This was just a false alarm. So until 1989, no top signal was found. And then these experiments, especially UA2, was able to set a higher limit of 69 GeV as the lower mass limit for the top quark. So the top quark, it turns out, had to be heavier than 69 GeV after CERN had looked at possible ways of looking for the top quark. So CERN at that time was out of the running. Actually, I remember by that time I joined Fermilab in 1989. I was at Duke University from 1985 to 1988, working on charm quark physics, working on hadron nuclear interactions, and also on a collider experiment, which is looking for quark-gluon plasma. But in 1989, I moved to Fermilab and joined Fermilab, and immediately joined the D0 experiment because I wanted to look for the top quark. And I remember very well a seminar by one of the scientists from CERN who was working on these experiments at CERN, UA1, UA2 experiments. And when they announced that they had set a mass limit of 69 GeV, and there was no way that the CERN colliders can reach for top because top seems to be too heavy. We were all elated because it was our opportunity now to be able to go and look for top quark. So anyway, so Fermilab was the gateway to the top at this point because all other colliders around the world had looked for it, and the top mass seemed to be too heavy and out of reach for any of the colliders except the Fermilab Tevatron. When I talk about Fermilab, I have to show this iconic Wilson Hall, the one that is designed by our first founding director, Bob Wilson. So I just wanted to show that. So the accelerators at Fermilab, of course, starts as it should in any high energy accelerator laboratory with particles being accelerated in sequence. You first accelerate protons to some small reasonable energy. We have Cockcroft-Walton, which accelerates protons to 750 kilo electron volts linear accelerator. Then accelerates it further to, it used to be 200 MeV, and then we upgraded to 400 MeV. Then there is what's called a booster synchrotron, which accelerates protons to 8 GeV. And then the 8 GeV protons go into the main injector. We used to have what's called a main ring in the same tunnel as the tevatron, which was later on replaced by main injector, but they both had 120 GeV, 150 GeV operations. And using those protons, then we create p-bars, the antiprotons, and then antiprotons are also accelerated then in the same main injector or main ring. And finally, the protons are accelerated in the tevatron to 980 GeV. So this is the accelerator chain at Fermilab. This shows the tevatron tunnel with the main ring on the top, which was the original accelerator that was built, that was accelerating particles to 400 GeV. And then the tevatron, which is at the bottom, was built with superconducting magnets. And in fact, the superconducting magnet technology was first developed at Fermilab and then adopted elsewhere, including at the LHC. The tevatron is a circular ring with 6.5 kilometers in circumference, and it operated from 1985 to 2011 and operated at center of mass energies of 1.8 TeV. In fact, in the beginning, it was 1.6 TeV to almost 2 TeV, so 2 trillion electron volts. So this is an aerial view of Fermilab, which shows the tevatron ring, the 6.5 kilometer ring, and then the main injector, which I mentioned, and booster and the antiproton. And I also show the positions of the two major collider detectors, the CDF and D0, which made the discovery of the top quark. And you can see Chicago, which is about 35 miles from Fermilab, and you can see the skyline of Chicago, in fact, from the Wilson Hall higher upper floors. You can, on a good day, you'll be able to see some high buildings from Chicago. So let me just say a few things about the creation of various particles in collisions, detection, and discovery. Particle collisions at very high energies can create lots of all sorts of particles via E equals mc square. You collide protons and protons, or protons and antiprotons, and all the energy that these particles have. In the case of the tevatron, 1 trillion electron volts, 10 to the 12 electron volts. Energy is all in a tiny, tiny volume. And then this energy density then can create all sorts of particles. So these collisions create new particles, which is kind of illustrated in the figure at the bottom here in the picture. And you can, once in a while, you can create some extraordinary particles such as the top quark or the Higgs boson. So what we do with these detectors, which kind of surround the collision points in a cylindrical geometry, is we track, identify, and measure particles. By measure, I mean measure their 4 momenta, their momentum as well as their energies. And also we try to identify what kind of particle it is. So detectors at the colliders are very large, and they're multi-layered, multi-system detectors surrounding the collision region. They're many stories high, thousands of tons in weight, and then millions of electronic readout channels. Now it's getting into hundreds of millions and more. And they have multi-tiered data acquisition systems. They produce photographic-like pictures, as you see, for each collision event. So here I again show a detection of particles from collisions. As I said, the detectors is built in multiple layers, and each of the layers may use different technologies. And so we want to detect particles that are coming out of the collision. And some of these particles are decays of heavier particles like the B quark or the CHOM quark, which become hadrons or composite particles after they're produced in these collisions, and also the top quark or the Higgs boson. And then they decay immediately, very quickly. And then we produce all sorts of other standard model particles from these decays, photons, electrons, muons, and hadrons, as well as, hadrons, which are, protons, neutrons, and kaons and pions, and so on. So all these particles have different way of interacting with the detector layers, and therefore we can identify what particle it might have been. For example, muons go through most of the detectors, and therefore they are identified in the outermost layers. Photons have showers in the electromagnetic calorimeter, but they don't have any tracks because they have neutral particles and so on. So based on this, we can detect what kind of particle it is, measure their energies and momenta, and then their angular distributions and so on. So here I show just the pictures, photographs of the CDF detector, the collider detector facility, which was the first detector that was installed and commissioned and started taking data even before the D0 detector. And they emphasize different technologies and strengths. The first collisions at 1.6 TeV energy in the Tevatron collider at CDF was recorded in October of 1985, and then the energy was raised to 1.8 TeV a year later. So CDF had already was ahead of D0 and had already produced some results, physics results, in 1988. In 1992, D0 joined CDF for the historic collider run 1. That's when D0 got its first data. So I also want to mention that the high energy physics experiments, because of the complexity of the accelerator and the detectors that we have to build, it requires a lot of expertise from a variety of scientists, engineers, graduate students, postdocs. So it's usually CDF and D0 used to be hundreds of people, as you can see here, CDF collaboration picture and then collaboration picture of the D0. And I want to also recognize here that D0 had several members from India, colleagues from Punjab University, Delhi University, Tata Institute of Fundamental Research, and so on. So these collaborations started out to be international collaborations right from the beginning. So let me just say, how do we find these new particles that we're looking for? Top quark, which we had not seen before, but we had seen other kinds of particles and what their signatures would be in detectors. So we look at these events, collision events, which we reconstruct by reading out the data from all the detectors that we have, and using that information from the detectors by generating these tracks, measuring their momentum, measuring their charge, the magnetic field, and identifying whether they are electrons or muons or photons and so on. So you get a lot of information from the detector data that you accumulate. So using that information, you can then see whether the event that you have satisfy some expected or characteristics of particles, or is it unexpected? So you could look at the events topological and kinematic information that you reconstruct from the detector data to see if there are events that look different from your normal standard model events. You can also then make plots of various distributions of quantities, transverse energies of decay products from some particles, and therefore you can look at transverse energy of various leptons, or some of the transverse energies, or you can calculate the invariant mass of combinations of objects, and then you can look for a bump or a peak in the distribution. So these are two ways of looking at trying to find new particles. So now let me say something about top production and decays at the Tevatron. At the Tevatron, top quarks are dominantly produced in pairs. That's the dominant production, TT bar. So a top quark is always, most of the time, is produced in association with an anti-top. The single top production has much lower rate of production because that's produced only through electroweak force, whereas the top pair production is through the strong force. And the top quark mostly, as it's gotten heavier than the W boson with all the limits, we started looking for top decaying into a W boson and a B quark because it's heavier than W. It's, you anticipate that it could be decaying into a W boson and a B, and the standard model predicts what decays are allowable and what the rate of productions could be, and what the characteristics should be. The W bosons then decay into a lepton and a neutrino, corresponding neutrino or anti-neutrino. It can also decay into a quark and an anti-quark, that is a quark pair. And these quarks then become jets of particles. They, through vacuum polarization, other particles are created as these particles come out of the collision, and then they come out into the detector as stream of particles. So they are usually called jets. So you have quark jets of various kinds, B jet, and so on. So so depending on how these W boson decays, you have different decay modes that you can look at to look for the top anti-top events, which are shown here. And out of these events with one W decaying into leptons and another W decaying to quark anti-quark pair happen to be kind of the golden channel for discovery, because they have a modest rate of production, also very moderate background. Whereas if both Ws decay into leptons, then the rate of their production, the rate of the decay products that you see to dilepton events is going to be much smaller. So we used the lepton plus jets channels as the golden channel for discovery. So the several other processes, so-called background, that are not containing top quarks can mimic the signature of the signal events. So we have to set criteria to select these candidate events and see if there is an excess, and look for a mass peak, whether we see, when we calculate the mass of a top quark using the kinematic quantities we have measured, do we see a mass peak as well? So we started getting very interesting events very early in the Tevatron run, after D0 joined the run 1 at the Tevatron. So in September 1992, for example, CDF had this beautiful event, which is textbook event, where you see the collision, and then you see some jets, and then you see an electron, and there is some missing energy. Neutrinos hardly interact with matter. You need a lot of matter to be able to find neutrino interactions. And so we measure them in colliders as missing energy. When you measure everything else, all other particles, you can look what missing transverse energy there is. And then there are B quarks. Now, these top events, they have top and an anti-top. So there are two top quarks, and each top quark decays into a W and a B. So there are two B quarks, and the B quarks, before they become a stream of particles that are pulled out from vacuum and become a jet, they travel a small distance from the primary vortex. So they actually appear with a jet coming out of a secondary vortex. So the secondary vortex is displaced from the primary vortex. So this is a wonderful way to tag B jets. So if there are two B jets there, even if there is one, but if there are two B jets, then it gives you more confidence that this is coming from possibly a top anti-top event. So CDF had this special silicon vortex detector very close to the collision region, which actually could measure these, identify these secondary vortices, whereas D0 in the first run did not actually have this silicon vortex detector. So we had to use other quantities, the kinematic and topological quantities that we measured to be able to select top quark events. In 1993, D0 saw a golden dilepton event, and which had two Ws decaying into nu and mu nu, so an electron muon event. And we did some multiple analysis to actually see that this event is a very top-like event. It's it's most likely a TT bar candidate, and the signal to background ratio from our analysis showed that this is 10 times or 18 times more likely to be a TT bar top anti-top event than a background event from a Z, a decay, or from WW. So I want to also say that in 1992, CDF, since we were getting all these beautiful events, and so we were getting excited that we may be seeing all these top quark events now, and TT bar events are being produced, and we are seeing the top quark. But in order to claim discovery, of course, we have to have enough candidate events to make sure that we are not fooling ourselves and fooling the world, that some background event may have fluctuated to look like a TT bar event. And so until we get enough statistics of these signal candidate events, we cannot claim discovery. So in 1992, CDF set a limit of top mass greater than 91 GeV, and later on in 1994, D0 sets a limit of 131 GeV. And the race between CDF and D0 now heated up because now there are no other competitors. It was between CDF and D0. So just a few things about separating signal from background. It's like separating a needle from a haystack, because the background events, which are not top anti-top events, are huge. And so you have to select few events, handful of events from this huge amount of data that we have. So as I already said, if you have two B jets coming from B quarks, that is a very good way to tag the B jets. CDF had a secondary vortex detector. As I said, D0 used other means. The other characteristic is that these top quark events would have very high energy leptons, electron, muon, are tau, and jets also with high energy or high missing transverse energy, and also missing transverse energy when neutrinos are present. So we used to use these quantities also to separate signal from background. By April 1994, CDF thought that they had enough candidate events with small enough estimated background that they went ahead and announced evidence for top quarks being produced at the tevatron. And the probability for any background faking the signal was about 0.26%. They had 12 candidate events, and they calculated a cross-section, which is a measure of rate of production of top anti-top events, to be 13.9. The problem is, of course, this cross-section that they measured was 2 times what the standard model had predicted the cross-section would be. So even though they claim 2.8 sigma significance, it wasn't clear that whether they had just gotten lucky that the statistical fluctuation gave them a lot of signal events, or whether their background estimate was incorrect or underestimated. D0 at that point had 9 candidate events and had about 3.8 plus or minus 0.9 events, and found the probability from background fluctuation to be about 2.7%. So it was 1.5 sigma significance. So I want to just mention that at this time, around that time in the late 1980s, actually already, there was a renaissance in neural networks. So artificial intelligence, you hear a lot about AI. There's a lot of buzz on AI and machine learning. But in late 1980s already, we were looking into neural networks because effective algorithms for training artificial neural networks had been rediscovered. And since CDF had the advantage of silicon vortex detectors to tag B jets better than D0 could, CDF did not really require any advanced analysis techniques, whereas D0 desperately needed advanced analysis techniques in order to improve their signal to background. So we had to become more efficient and competitive with CDF. We needed these any advanced technique that would give us better signal to background ratio or better efficiency for signal discovery. So I actually adopted and developed the use of neural networks to discriminate top quark events from background events in D0 starting already in 1990. And here I've shown a neural network schematic where you have various inputs that you would want to provide, various quantities that you measure, and then you have hidden layers with hidden neurons, which develops the representation of the inputs and maps to an output, and you can train the neural network to give you some desired output, target output, say for signal as 1 and for background as 0, which is what we did. And we use series of networks. And you can see that the distribution for a simulated Monte Carlo top quark events, you get a distribution that peaks around 1. And for background, you have distribution that peaks around 0. So then you can more effectively process your data events through this trained neural network, look at the distribution, apply cuts, and you can actually get much better efficiency to separate signal and background that way. We were using otherwise these conventional rectilinear cuts, which actually keeps more background and loses more signal. So that was actually, advancement that was going on in parallel as we were looking for the top quark and I was applying it. I and a few of my colleagues formed a multivariate and machine learning group and were applying this to top quark searches. By March 1995, both CDF and D0 had come to the conclusion that they had seen enough candidate events, and so the analysis internally, even though we used advanced techniques, the collaborations wanted to be conservative in the discovery papers and used simple cuts for event classification. So I've given here the results at the time of the discovery from CDF and D0. CDF had 56 events with an estimated background of 23. And their cross-section was now 6.8 picobond, whereas at evidence they had 13 picobond. The top mass was 176 plus or minus 13. D0 also got a 4.6 sigma significance with 17 events, candidate events, and the background was much less because we were cutting applying very strict cuts, and the cross-section is similar to sigma. But since our resolution for selecting signal events was not as good as CDF, our mass measurement was not as good. Anyway, so the top quark was finally discovered 18 years after the B quark discovery. I've lost some words here, I see. It was found to be very heavy. We finally ended up with measuring the top mass to be around 175 GeV. I'll show you some results from the top mass measurement. And it's extremely short-lived, with lifetime of 10 to the minus 25 second, which means that top quark is the only quark that actually decays almost instantly after it is formed. It has no time for the so-called QCD hadronization to take place, to become dressed up and become a jet. So it decays as the quark into W and B bosons, W boson and the B quark. And so using the decays of the W boson and the B, you then measure the properties of the top quark directly. So here is the Ramsey Auditorium full with people, both from collaboration and all those who are excited about the top quark discovery at Fermilab on March 2nd, 1995. In the inset is our spokespeople, and in the middle is the Fermilab director at that time, John Peoples. So the top quark mass measurement, as I said, CDF had this beautiful silicon vertex detector in run one, and therefore could select top events more easily. And they, by 1998, they had measured the top quark mass to be 175.9. plus or minus 4.8 plus or minus 4.4 using lepton plus jets events. Now D0, then I further pushed with a few other colleagues to actually use the advanced analysis methods, especially neural networks and likelihood methods, to select top quark events for top mass measurement. And this did the magic for us. So we measured actually with the comparative sensitivity to CDF in run 1, a top mass of 173.3 with the errors here, which were also comparable to the CDF result. And interestingly, the current best measurement is about 173 GeV still. So I'm very proud of the top mass results that we produced at that time, at the time of discovery in 1996, shortly after the discovery in 1996, 1997, using neural networks. So the picture looks like this. If you look at the quark and lepton masses, the top quark is basically a monster. It's huge, and it's famously said that the top quark has a mass of a gold atom because it's 173 GeV. So in circa 2000, so this was the picture. We had filled all the gaps in the quarks and leptons and the force carriers. The top quark had been found in 1995. And the tau neutrino was also directly observed at Fermilab. So in 2000, this was also, this gap was also filled. So the 3 generations of matter particles and force carriers were all found by 2020. So far, I had kind of ignored the Higgs boson, even though I mentioned it in the very beginning. Now, let's not forget about, we can't forget about that anymore. Without the Higgs boson, the standard model does not work, because in the standard model, all the elementary particles would have 0 masses, the matter particles, if and the gauge bosons, if the Higgs field doesn't give it the mass. So here comes the God particle. Where did this notation of God particle come from? It came from, again, Leon Lederman, who wrote this book with the title, The God Particle. If the universe is the answer, what is the question? So he discusses in his book why these pursuits of elementary particles are important, and then discusses about the Higgs mechanism and why the Higgs boson and finding the Higgs boson is important. So the elusive God particle is the Higgs boson of the standard model. And the standard model has been remarkable. It has been confirmed to great precision in hundreds of measurements, but it, of course, requires this Higgs field to break electroweak symmetry, giving masses to the W and Z bosons, and then quarks and leptons also get masses from the Higgs field. So after the discovery of the top quark, Higgs boson became the most wanted particle, and intense pursuits at the Lab Collider and the Tevatron started before the LHC. So there has been this competition and collaboration between CERN and Fermilab for the top, and then now here with the Higgs. So these are just portraits of Higgs theorist Peter Higgs, to whom the Higgs mechanism is named. He proposed that and developed the theory in 1964. And then a number of other theorists who also did seminal work on the Higgs mechanism. So somebody had produced at the time of the Higgs discovery this beautiful cartoon which explains how to think about the Higgs boson and how the Higgs field gives masses to the particle. So I just wanted to quickly go through it. So the Higgs field is supposed to be all pervasive. It fills the space. It's everywhere. And how does the Higgs boson come about? So imagine a big ballroom full of people waiting for things to happen at the party, waiting for some VIP. And then here comes somebody, and then, at the door gives some information, some news, or some secret or whatever. And then everybody in the big room want to know what the message was, what the new information was. So people clump around to find out what the news was, and that travels across this. So this is like the Higgs boson is like the excitation of the Higgs field, local excitations of the Higgs field. So that's how Higgs boson manifests the particle. Now, how do particles get mass while going through the Higgs, through the Higgs field? So here comes a celebrity, a VIP, and people are interested in talking to the VIP. And so they again clump around the person, the celebrity. And so this is an analogy for how particles moving through the Higgs field can get mass. The person here, this VIP, gets slowed down because people are trying to talk to him or her, and so that slows the motion, and so that friction causes and it's like an effective mass. So that's how particles get mass. So it's a nice cartoon. So I want to say a couple of things about pursuing the Higgs at the Fermilab Tevatron. Having discovered the top quark, Fermilab experiments, really hoped that we could discover the Higgs boson before the LHC came on. So there were intense workshops and studies made which yielded ideas for an aggressive pursuit of the Higgs boson at Fermilab before the LHC started. And it was found that if we got 100 times more data for both CDF and D0 experiments, we could have clear evidence for the observation of the Higgs boson. And extensive upgrades to the Tevatron complex followed. Actually, I didn't leave the D0 collaboration, but actually spent most of my time directing and managing the upgrade project of the entire Tevatron complex to make sure that we were able to get, huge luminosity increase at the Tevatron collider. And I also developed a strategy for discovering a low mass Higgs boson at the Fermilab Tevatron with a few of my colleagues. And this basically shows that using specific channels of the Higgs production and decay, we could, if we used the neural networks or machine learning techniques, we can actually observe the Higgs boson at the Tevatron, or at least get evidence for it with half of the data that was initially thought of. And so this was also an important reason why we were very much interested in upgrading the Tevatron and trying to compete with CERN to see if we can at least find the evidence. The evidence did come from the Tevatron data, but not until just before the discovery at the Large Hadron Collider. But however, we had throughout the run 2 of the Tevatron, we had various new measurements and observations, discovery of the single top, and then eventually Higgs 3 sigma evidence. But also measuring the top quark mass and W mass also provides constraints on the Higgs mass. So that's another way that provided information for Higgs searches at the LHC. So in 2006, even though the Tevatron was still running, I made the decision to actually stay on the D0 collaboration, but also join CMS experiment because I was too eager to be part of the Higgs discovery and I could not let it pass. So the Large Hadron Collider was, being commissioned, installed and commissioned, and then the detector CMS and Atlas detectors were being built in the early 2000s. So this is the Large Hadron Collider landscape. It's a 27-kilometer ring Basically, it was a LEP ring, the electron-positron ring that they already had, that was repurposed for proton-proton collisions. So here, it's certainly a scientific and technological marvel with 27 kilometer circumference compared to 6.5 kilometer circumference of the Tevatron. This now uses more than 10,000 magnets. It has the largest cryogenic system in the world, and the magnets are cooled by superfluid helium to 1.9 degree Kelvin, whereas the Tevatron was at 4.1 degree Kelvin. So, and the LHC is installed at a depth of 70 to 140 meters below ground. Here is a schematic diagram of the CMS detector. This, as I have said before, shows around the beam pipe the detectors with multiple layers, different types of detectors, silicon detectors, which are trackers at the core of the detector, and then you have various calorimeters for measuring electromagnetic and hadronic decay products, and then the muon systems at the very end. So then the CMS, these are just pictures of the CMS detector. And when the detector was being assembled and commissioned, I used to take shift leader shifts and would go down to the cavern where the CMS detector was being commissioned, and it was just amazing to just stand there and see that the detectors that we're building were all being integrated, and it's just a beautiful and amazing feeling. This is after the detector was completely commissioned in 2009. We were taking shifts for taking data and testing the detector. So this was an all-female crew that on one night shift. So one of our colleagues who came by said, he wanted to take a picture. And so here is an all-female crew for a night shift at the CMS control room. As I said, these collaborations are large, and actually they are, of course, getting larger. We are becoming more and more, not just international, but global. So now CDF and D0 had several hundreds of people. Now we are becoming collaboration of thousands of people. I want to also note again that the CMS collaboration has several member institutions from India, and actually more institutions have joined since the CDF and D0 experiments. I think the IISc at Fermilab in Bangalore is also a member, and some of the IITs, and of course TFR, Punjab, Delhi, and a few other universities, University in Pune, and so on. So the Higgs bosons are produced dominantly by gluon-gluon fusion in the LHC. There are two decay modes that were important for discovery: Higgs decaying into the final products of 2 photons and then 2 Z bosons. So I put the diagram for the Higgs to ZZ decay, because this is a very clean and beautiful decay, which we used in the discovery. And also this is a very nice channel to make various measurements. And Z decays into 2 leptons, either electron pairs or muon pairs. And by the time of the LHC and these experiments, both CMS and Atlas extensively used multivariate analysis, as well as machine learning techniques such as neural networks, boosted decision trees, and so on, in identifying all the collision products and event classification and so on. I wrote a pedagogical review for annual reviews of nuclear and particle science just before the Higgs discovery 2011, as we were getting towards the discovery, to make sure that my collaborators and colleagues understand and actually will adopt these machine learning techniques, which gave us a huge improvement in the ability to efficiently find these Higgs boson events. So here is a celebrity event, which is a Higgs to diphoton candidate. The ones in green shown here are the photons. Here is a Higgs to ZZ to 4-lepton event. And you can see the 4 leptons beautifully. And here are the peaks. The bumps were there, the mass peaks. So in the Higgs to diphotons, in the top from CMS and Atlas, and then from Higgs to ZZ to 4 leptons. So they both had peaks around 125 GeV. So here is the CERN auditorium on July 4, 2012, when the Higgs boson discovery was announced. Fabiola Gianotti, who is the director till the end of this year, she was the Atlas spokesperson presenting here. I was sitting here, actually, Ralph Hoyer and I were standing outside welcoming all the guests who were coming in. And so Peter Higgs came and everybody were trying to talk to him. And so a lot of people were getting clustered around him and people were taking pictures. And as Peter Higgs was coming towards us, I was telling Ralph Hoyer, who was the director at the time of CERN, I told him that, Ralph, here is the Higgs mechanism at work. And so when Peter Higgs came to us, Ralph said, Peter, now I understand the Higgs mechanism. So that was a beautiful moment. So anyway, so there was a lot of excitement all over the world. So lots of magazines carried how important the Higgs discovery was and that this was a breakthrough. So the Standard Model has been triumphant with the discovery of the two heaviest elementary particles, the top quark. In fact, that is the heaviest. It's heavier than the Higgs boson. And so we had completed the Standard Model of particle physics, and Francois Anglaire and Peter W. Higgs deservedly got the Nobel Prize. The big collaboration, CMS and Atlas, we ended up getting recognized by the European Physical Society in 2013, and with the Breakthrough Prize in Fundamental Physics in 2020, also shared with the other two LHC collaborations, LHCb and ALICE, for various contributions. So then in the US, we decided we would celebrate the Higgs boson on Capitol Hill. We were requested by some members of Congress to go and have a celebration and have Joan Candela, who was the spokesperson for CMS, who was a US person. So he gave a talk. Here I am kind of introducing, emceeing the event. So this was a beautiful event that we had celebrating the Higgs. So the discovery of the Higgs is the discovery of the new millennium, we could say, in 2012. But it's not clear if it's the last missing piece. It was the last missing piece in the Stern model. But is it the last elementary particle, or is it the harbinger of new physics? Does it fully explain the electroweak symmetry breaking, which gives masses to the W and Z bosons, and also then masses to all the other particles? Is it elementary or composite? Are there more Higgses that we might find? So we are getting a lot more data, and so new results. Here I show just a picture again of the Higgs to ZZ to 4-lepton, where you can see now, the peak for the Higgs, which is prominently much higher and much nicer than what we had at the discoveries. And we have been also measuring coupling strengths with various particles, rates of productions of different decay modes, studying a number of things with Higgs, and also looking for di-Higgs production and new particles that may couple to Higgs. So what's next? The LHC is being upgraded for higher luminosity, that you might know. We will have the high luminosity LHC to produce 2 orders of magnitude more data than we had for the Higgs discovery. And then we are also looking forward, as you can see, from B quark discovery to the top quark discovery from 1977 to 1995, we had 18 years gap. And then from 1995 to 2012, another 17 years. So, so these projects take a long time, a lot of persistence. And so we're already planning an electron-positron collider, a Higgs factory for making precision measurements of the Higgs so that we can understand the Higgs field better. Also, there are plans for higher energy hadron collider and possibly a muon collider. So I just want to leave with a couple of slides. I want to say that the top quark and the Higgs are deeply connected. The Higgs boson is central to our very existence. The Higgs field gives masses, as I said, to the Standard Model particles. And without the Higgs field, the electron, for example, will be massless, and so atoms cannot form, and therefore no chemical bonds, no chemistry, and no life forms, and so on. So the Higgs field is very unique. It's also the only scalar field that we know, and it's the only scalar fundamental particle that we know. And so understanding the Higgs self-coupling and Higgs field is vital. The studies of associated production of top quark pairs with the Higgs also may help us to understand the nature of the Higgs boson itself. So the top quark and the Higgs boson may both play a key role in new physics beyond the Standard Model. So these are future collider options that are under consideration. Of course, CERN is considering 91-kilometer ring in the Geneva area around at CERN for an electron-positron Higgs factory. It's called Future Circular Collider, which can then eventually host a 100 TeV proton-proton collider. There are also plans for, not plans, there were plans for a linear collider, and that could be CERN's option if the FCC does not go forward. Japan was interested, but nothing has happened at the ILC. US actually led the global design effort there. China is interested in a circular Higgs factory as well. Fermilab is making efforts to build a muon collider on Fermilab site, a multi-TV muon collider, which has several interesting advantages and combines the advantages of both the hadron machine and lepton machine. So with that, let me summarize that the race for the top quark and the pursuit of the Higgs boson at Fermilab and at CERN had been breathtaking, and the discoveries are monumental landmark discoveries. The saga of elementary particles that began at the turn of the 20th century culminated in the development of the Standard Model and the discovery of all the particles of the Standard Model about a century later. The Standard Model of particle physics is one of mankind's magnificent intellectual achievements. New physics beyond the Standard Model is needed to solve many other mysteries, such as neutrino masses and mixing, to explain dark matter, baryon symmetry in the universe, and so on. So we are working towards next big machines. Of course, we still have high luminosity LHC, starting in 2030 or so, but then in the 2040s, there will be hopefully an E plus C minus Higgs factory, and beyond that, a much more powerful proton-proton collider or a multi-TV muon collider. So thank you, and I would be happy to take any questions or comments.
Thank you very much, madam. Now there is time for some questions. If you would like to ask any questions, please raise your hand and ask one by one, but be brief in your questions. Okay. Any questions? So let me start with one simple question. You mentioned that the lifetime of this top quark is around 10 to the power minus 25 seconds. Briefly explain how this lifetime can be measured. What kind of measurements can give us the lifetime of this top quark?
The hadronization time is of the order of 10 to the minus 23 seconds. You can, for example, the charmed quark and the B quark, they actually, you can measure their lifetimes with the displaced vertices. And the top quark, so you can predict the masses, the time, the lifetimes of these particles. 10 to the minus 25 second is much smaller than the hadronization time of 10 to the minus 23 seconds. So in fact, if it was higher than that limit, you can infer that from making some measurements of the width, etc., the width of the width of particles and so on. But the The thing is that you would have found the TT bar bound states if the top quark mass was higher than 10 to the minus 23 seconds. And we do have some interesting new results which shows that that the top anti-top produced at the LHC may have some small probability that there might be quasi-bound states of TT bar that's formed. But basically, from the properties, from the fact that it's that heavy, and from using the Stern model theoretical framework, you can calculate these lifetimes, and it turns out to be that that you do see the top quark directly decay in such a short time that agrees with those.
Thank you. Dr. Usha Devi, would you like to ask a question? Please go ahead.
Hello. Thank you. Thank you for a wonderful talk. And I teach particle physics in Bangalore University, very general, up to 1964 kind of standard model. But I want to just know something like in 1950s, people still were doing cosmic ray designs, and then used to predict for new particles and so on, for strange particles and so on. I just want to ask you, are there any kind of predictions, like if we only depended on cosmic ray physics or some cosmological events, could we have discovered Higgs or top quark or anything that is just through cosmic ray physics?
No, so the cosmic radiation, as you may know, the muons were discovered in cosmic radiation, a positron too, I believe, and then the charm, the strange quarks, I mean strangeness, the kaons, for example, were also discovered in cosmic radiation. And so if you, I mean, you might know that the quark theory initially, the eightfold way, used the three quarks, right? U, D, and S.
Right.
And and then eventually it's because of because of when the strange quark and the muon were discovered, there was, of course, this expectation that maybe there are second generation quarks, right? And the charm was predicted. Then the charmed quark onwards, particle accelerators were critical to produce these particles in enough numbers to be able to. And, cosmic radiation, you may have once in a while very high energy particle that interacts somewhere with some, and there is, so you need really intense sources, man-made source of these high energy particles that are colliding. And as you know, even fixed order experiments went out of fashion or practical utility, in fact, in looking for these heavier particles, because these particles, the B quark and the top quark and then and Higgs, they were all so heavy that you cannot get enough center of mass energy in the fixed target experiment, right? So then the collider concept actually helped to yeah.
Right. Thank you. That is only thing is predictability. That is, if at all one restricted to some cosmological events, there is there any possibility how meek it is? Fine.
Yeah, but the standard model actually, it was kind of interplay between theory and accelerator developments, right? So something was seen in the accelerators that confirmed the theory, and then the theory was further extended. So it has been back and forth. When the B quark was discovered, then of course we knew that because the standard model theoretical framework was there, that the isospin doublet should exist. In fact, the quark model, of course, also has this idea of the isospin doublet that was introduced, right? And so when you had the strange quark, then you can predict what, that it has to have an isospin doublet, and then it was predicted. And so there has been a very close interplay and push from both from the theory side and the accelerator side. But particle accelerators were critical for the development and completion of the standard model.
Yeah, I agree. Thank you very much.
Question, Keshav Murthy, Professor. Please ask your question. Keshav Murthy, Keshav. Okay, I have two general questions. One of them, is there any proof that we should have only 3 generations of quarks and particles? Any kind of a proof? And secondly, is it possible to predict the neutrino masses using the Higgs mechanism?
So it's a good question. These are good questions. So there is no rule. I mean, so the standard model doesn't say that there cannot be a 4th generation. So in fact, we did look for T prime and B prime. We kind of got, particle physics started after Strange. We started talking about charm and beauty and truth and so on. And then we changed beauty and truth to B and T, bottom and top. And then the 4th generation, of course, we thought, why not? We can look for it. And so we have looked for B prime, T prime particles. So it's not excluded. And the neutrinos, this neutrino masses is what might need the new physics beyond the standard model, right? So there are various, hand waving, there are various mechanisms, seesaw mechanism, you might know about that. So there are other mechanisms that have been kind of, suggested, proposed, but I think we need to do more experimental work on the neutrinos as well to give theory more information. So this is why there are now these big neutrino experiments. You might know LBNF Dune and Hyper-K and so on, which are trying to make measurements in the neutrino sector, very precise measurements, which might actually provide more, information on these various mechanisms.
Thank you. Keshav Murthy.
Yeah, are you able to hear me? Okay. Yeah, it was an excellent presentation from a person who was directly involved. So that's a real fortunate thing for all of us. You are involved in both the top quark production as well as the Higgs boson top quark interaction. My question is, of course, there are many questions which I might like to ask for clarification. What is the kind of data that you depend on when you are doing that? In fact, you said that the background, I assume from my background, that background means, different channels giving different types of, data. So it's a kind of an inverse problem. Is it an inverse problem? It's a kind of an inverse problem, I guess, unfolding.
I mean, there is unfolding that's done in certain measurements, but when we're talking about signal and background, there are a lot of standard model processes that produce lots of particles. I mean, most of the collisions produce just jets of quarks and gluons, multi-jet production, it's called. So you have 2 protons banging into each other, right? I mean, these protons are actually, I mean, I showed a very simple picture of proton containing up and down quarks, right? 2 up quarks and 1 down quark. But actually, they are like trash bags of lots of things happening inside.
Yeah, I know.
Because they have gluons. And so when 2 protons collide, you can have quark from one, hitting a gluon from the other, or gluon interactions and so on. In fact, at LHC, the energies are so high that the Higgs TT bar, the gluon process actually gives a very high rate of production for many of the processes as well. So most of the products of these collisions are actually multi-jet is one of the biggest background. That is outgoing a number of quarks and gluons coming out of these collision points. So you can have two jet events, famous dijet events, but that could also be coming from something that is formed, some new particle that then decays into two jets, like Higgs can decay into BB bar, for example. And then you have other kinds of processes which are just producing, these quarks and gluons coming out of the collision. So they are just simple multi-jet events, two jet events, three jet, four jet events, and we have to actually have a Monte Carlo simulation using standard model diagrams, Feynman diagrams, for example.
Yeah.
And then
actually,
there are other processes like W plus jets, for example, or WW Z plus jets. So there are lots of standard model processes that come from these collisions, right? So it's like throwing a dice, and each type of process, I didn't put any Feynman diagrams here because I didn't want to scare the students with.
I'm going to ask about that too. This uniqueness of the solution is something which I was wondering. I think it was a great achievement to achieve uniqueness of the solution, isn't it? And
you mean separating signal from background?
Yeah. And then the other thing is, of course, you mentioned Feynman diagrams. I assume that your machine learning models, you have to, the experimental part of the data may be very little. So you may be depending on calculations. Feynman diagram is okay, but this is a Feynman diagram with changing coupling constants, right?
I mean,
because of the asymptotic theories that you use. Otherwise, you cannot use Feynman diagrams here.
I mean, there are theoretical calculations. There's a phenomenology is a cottage industry. I mean, you have to use next to leading order, next to leading order, and n-cube leading order calculations for many of these, especially when you have multiple jets coming out, because gluons radiate other gluons. So especially in hadron colliders, it's a mess. You have lots of gluons all over the place, and so these it's not an easy thing. In fact, when we were doing top quark searches, actually predicting W plus jets background was not very easy. So there were theorists who were, I'm an experimentalist, so we make these detectors and then look at what comes out.
I know.
Try to use theoretical framework and their predictions and their calculations. Once upon a time, we used to do some of the theory ourselves, but then later on it became more specialized that they had to take into account all these, extra next to leading order calculations had
because
to be
they
made.
would give some uncertainties, no? So some uncertainties
there
would
are
come out of
theoretical uncertainties, and in fact, as you point out, most of the time these machine learning models are trained on Monte Carlo, the simulated events. But there are cases where we actually use data also. So an example I can give you is in the TT bar events where we have all hadrons. Well, so W decays to quark anti-quark pairs, UD bar or CS bar. So you have two quark jets from each of the Ws decaying, and so you can have then 6 jets in the TT bar final state. So TT bar, both tops go into W and a B, and if both Ws decay hadronically, you end up with 6 jets. And of course, then you can probably have some gluon radiation and so on. So what we did in that case, in the all hadronic case, is that we knew that the multi-jet background is horrendous. It's very high. So even though the signatures are the same, if you choose 6-jet or 5-jet events, we actually trained the neural network using our data, which satisfies.
Recording in progress.
Sir, the first one is that being a 7th standard student, a youngster, can I imagine that inside the nucleus which has protons, electrons, neutrons, but does it also have an unknown world or universe like Big Bang? And again, inside that it has hadrons, leptons, quarks, and Higgs.
So the nucleus we know has protons and neutrons, right? I mean, so actually, if you take the simplest atom, hydrogen atom, the hydrogen atom has a nucleus which is just a proton. Okay. But the proton itself has, as I said, it has got these up quarks and down quarks, 2 up quarks and 1 down quark. And it can also has these gluons. And then the another interesting thing is that these the other particles, such as the charm, anti-charm, strange, anti-strange, they can be created inside inside these particles for a very, 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 very tiny fraction of a second. So you won't mostly, you won't see the effect of those things, but these can be coming from the C. They're called C quarks. So they have some existence, some tiny probabilities for existence of these other types of quarks themselves. So that's why we kind of say that the protons and neutrons are composite, and then you have to look at these quarks, and then are the quarks really elementary, or the fundamental, or do they have something else in it? So
Okay.
Sir, one more question. Rishikesh Narayanan, I think we can make it as the last question.
Narayanan, please ask you. Okay, please ask.
Mm-hmm. Yeah. Mm-hmm. That's a very good that's a very good question. The Higgs the top quark is produced by the strong force, as I said. It has a dominant production through strong force, right? So its rate of production is higher, whereas the Higgs actually is produced through electroweak processes. And it if I showed you the Feynman diagrams, you would see the Higgs production from gluon, for example, goes through what's called a top loop. So it is produced through a top loop through electroweak interactions. So therefore, the rate of Higgs boson production is smaller, much smaller than that of the top anti-top. So that's why, even though the Higgs boson was less massive, its rate was smaller.
Okay, thank you. Now, our Joint Secretary, Dr. Rudraswamy, to propose a vote of thanks.
Okay.
We are running out. So
Thank you very much, sir, for extending this great opportunity. It is indeed a great honor for me to propose a vote of thanks on this special occasion. I am very much delighted to know that Dr. Pushpalatha C. Bhat Madam is presently serving as a highly distinguished scientist at the highly prestigious and reputed research institution of Fermilab in USA, after obtaining PhD from Bangalore University under the able guidance of Professor N.G. Puttaswamy, the former Honorable Chairman of Physics Department, closely involving in this discovery of the top quarks in the study of Higgs boson, researching for new group of Fermilab Future Collider, and securing many prestigious international scientific awards. Madam, we are all very much benefited by your inspirational today's talk on tale of two discoveries, top quarks and Higgs boson discovery on behalf of Karnataka Physics Association. We are very much thankful to you, madam, for sharing your scientific achievements with us in today's talk. Thank you very much once again, madam. Thank you very much. So we are very much thankful to Professor. We are very much thankful to our beloved President, Professor